Okay, so today we will continue the problem solving sessions on chapter 1. We already solved the first four problems, and now we will continue with problem 5. So the belt in the figure moves at steady velocity v and skims the tops of a tank of oil of viscosity mu. Assuming a linear velocity profile, develop a simple formula for the belt power P required as a function of H, L, V, B, and mu. Neglect air drag. What power is required if the belt is moving at 2.5 meter per second over oil at 20 degrees with L equal to 2 meters, B equal to 60 centimeters, and H equal to 3 centimeters. So let us think about how to solve this problem. What we want to find here is the power. So mainly we need to find the power required to move the belt. Okay? So here, first, you should go back to the definition of power. How to calculate power? What should we do? Power is mainly force times velocity. Okay? And here, to find the force required, we know that we are moving the belt over an oil film. Okay? So we should overcome the viscous resisting force of the oil. This is why force F can be replaced by tau times, so it's tau times the area of contact with oil times velocity. Okay? And as we know, so here the shear is applied at this level here. We have shear at this level over which area? It's equal to the area of contact between the belt and oil. Okay? So here, they said that the length of the belt is L and we have a width of B. So if I draw it here, this is the contact area between the belt and oil. Okay? This area can be calculated simply by saying it's equal to B times L. This is the area of contact between the belt and oil. So now if I replace in the formula of power, okay, I should first calculate the shear stress tau. The shear stress tau can be calculated, as we know, by mu del V by del Y. And here, since we know that they said assuming a linear velocity profile. So since we have the assumption of linear velocity profile, then we can replace del U by del Y by simply V over H. Why we can do this? Because as you remember from last time, we have the velocity is starting from 0 and it ending by big V. So delta V is big V minus 0 and delta Y is H. So tau is simply mu times V over H, and then the contact area is B times L, and then we multiply by the velocity. So this is how we obtain the expression of power. It's mu times V squared times B L over H. Okay? Any question until here? Yes, H is the thickness of the oil film. So this is H. This is H here. Okay, it's the thickness of the oil film. So it's the thickness where the velocity is varying. So if I draw for you the variation of velocity, it's like this. So at this level, it's fixed. You have here a fixed wall. Okay, so you have a 0 velocity at this level. The velocity will start from 0 here and will increase until reaching a value of V at the contact with the belt, because the belt is moving at velocity big V. And since this is a fixed wall, So the velocity here due to the no slip condition is 0, and here we are maintaining a velocity v due to motion of the belt. So we are imposing here due to no slip condition with the belt a velocity big V, while here we are imposing a velocity of 0. So there will be a gradient of velocity inside the fluid, where the velocity will gradually increase from 0 to V due to viscous effect. Okay, so because of viscous effects, the viscosity will oppose the relative motion of layers of fluids with respect to each other. And since we have a linear velocity profile, then we will have a gradual increase in velocity in a linear way from 0 to V. Okay, so this is why when we say del V, let's say del V here over del Y. Okay, so because in general we said in Y direction we call the velocity small v, and in X direction we call it u. Sometimes in some problems they might use different notations, but it's fine. Okay, so just you should understand the concept. I should find the variation in velocity in this direction, which is del v by del y, and del v is equal to the variation in velocity, which is v minus 0 over the variation in y. The variation in y here is equal to the thickness of the oil film, which is h.